In this video, I want to look at continuous probability distributions. Continuous variables cannot have a probability mass function. The reason why? The probability that a given random variable is equal to some value a is equal to 0 for any value of a. So if I actually look at the probability of a particular point of a continuous distribution, it's going to be equal to 0. To get a rough idea of why this is true, let's consider the interval 0 to 1, and we want some random number in this interval. So some random number between 0 and 1. The probability that my random number is in any interval of a given length L is equal to L. So if I look at the length of the interval, then that tells me the probability that the number is in that interval. Well, a single number is in an interval of length 0. So that would tell me that the probability of that exact value is equal to 0. So let's take a closer look at these continuous probability distributions by looking at a particular case known as the uniform distribution. The example we previously did, selecting a random number from the interval 0 to 1, is in fact a uniform distribution. It was uniform in the interval 0 to 1. So we denote our distribution by u of 0, 1, letting us know that we're going to pick any random number between 0 and 1, and each number has an equal chance of being selected. So all subintervals of equal length are equally likely to contain the selected number. Let's start by figuring out the CDF for the distribution from 0 to 1. So as a reminder, the CDF is the cumulative distribution function, and it tells me the probability of everything that comes before. Nothing comes before 0, so for every value smaller than 0, the probability that it comes before 0 is 0. Everything in this distribution comes before 1, so for any value bigger than 1, the probability would be 1, since everything comes before the value of 1. So what we really want to consider is this idea of between 0 and 1 and what happens. Well, we know the probability of any given interval is the length of the interval. So for instance, the interval 0 to 1/2 has a probability corresponding to 1/2. The interval 0 to 1/3 has a probability of 1/3. 0 to 1/4 has the probability of 1/4, etc. So this actually turns out to just be x. The number that we're looking at is equal to the probability, as we can see here, the 1/2 and 1/2, 1/3, 1/3, 1/4, 1/4, etc. So this is my cumulative distribution function. While I do not have a probability mass function, I do have a probability density function for continuous variables. It's noted by PDF. This is a non-negative function that we're going to denote by f. And for the probability density function, the probability that a is less than x is less than b, so the probability that my number is between two given values, is the area under my probability density function f between a and b. So instead of actually just evaluating the function, we're going to look at the area under the curve. So I want to start by looking at some of the more common shapes of these probability density functions, and then we'll take a closer look at them. The first shape is symmetric, where it looks roughly symmetric across the center point, so I can draw a vertical line through the center. And my picture is not great here, but it should be the same on both the right and the left. This is the idea of a symmetric distribution. Next, we have a positive skew, also known as skewed to the right. In this case, we have a peak on the left and a tail on the right. So when we talk about skewed to the right, we're referring to where the tail is. So we have the peak on the left side and the tail on the right. Similarly, we have a negative skew, or skewed to the left. This one is going to have a peak on the right, and then a tail on the left. So the skew refers to which direction the tail is. We can also have bimodal, and bimodal would indicate two peaks. And they don't have to be exactly at the same height, but the idea is we have two peaks rather than one. So now we have some basic shapes for probability density functions. Let's consider what they actually mean. So here I have my symmetric distribution. And if I look at the area under this curve between 1 and 2, this actual area of the shaded region will be equal to the probability that x is between 1 and 2. And in the next video, we'll take a closer look at probability density functions and how to use them.